Okay, now in today's lesson, we're going to look at questions that concern hydrocarbons, past exam questions. And hydrocarbons could be the alkanes or the alkenes. Especially alkenes, there are quite a few questions in the exams. It's very likely to have questions on alkenes, and especially on the oxidation of alkenes, and also on isomerism because of the double bond. But nevertheless, let us start with a question on alkanes, which is not very common to find alkanes, but nevertheless, here is a question, and from one of the recent exams actually of this year. And let us see how it is phrased and how it looks like. Okay, so there are many different types of aliphatic and aromatic hydrocarbons. Name a naturally occurring source of aliphatic and aromatic hydrocarbons and outline how different hydrocarbons are separated from this source. Well, first of all, I hope aliphatic, I don't know, I'm not sure if this word is in the book, but aliphatic are all the hydrocarbons that form the chains, could be straight chains or branched chains, but not rings. Okay, so practically all the hydrocarbons that we come across in most cases in our questions are aliphatic. So aliphatic, in other words, are all the hydrocarbons that are made of carbon and hydrogen that do not form rings, non-rings. Whereas aromatic hydrocarbons are the ones, this one is mentioned in page 2 or 3. It's actually these hydrocarbons form rings, and they have bonds which are one single, one double, single, double, single. So they, in other words, a sigma and a pi bond kind of interchange. Okay, now, but let us go quickly through these questions. So where do we find this type of hydrocarbons? We find them in crude oil, of course. So here our answer will be crude oil. And if you answer petroleum, that will also be accepted. Outline of separation of hydrocarbons. They want you to say that they are separated according to the boiling points. So according to different boiling points. This is what, according to different, in other words, we rely on the difference in boiling points, different boiling point. That should be enough. Okay. Next, question B. When alkanes are heated to high temperatures in the absence of air, the molecules can break into smaller molecules. Oh, this is the famous cracking. This is a word that you need to know. This method of cracking is where we produce the smaller hydrocarbons, which are more useful than the big ones, through cracking. And the next question is actually also concerning cracking, and says, write an equation which describes the reaction occurring when heptane is heated in the absence of air to form hexane, butane, and ethene only. So in other words, we have to write an equation that involves heptane and all these products, hexane, butane, and ethene. I have them all. Yeah, so that's all that we need to do here. So there is the heptane. Yeah, and this, after cracking, breaks into these 3 items only. They say, fine with us. So this is the hexane, and what is this? Butane with 4 carbons and 10 hydrogens, and okay, ethene. Now be careful, that is not ethane, it's ethene. And now we need to balance it as well. Now we have 7 here, and here we have millions of carbons. So obviously something has to be, we need some coefficients here. Okay, 6 plus 4 is 10, and 2 is 12, and here we have only 7. If we place here a 2 now, we'll have 10 plus 4 carbons is 14. So if we place a 2 here to have also 14 carbons, let's see if it's balanced now. Now this will be 32 hydrogens. Let's see, do we have 32 hydrogens on the other side? 14 plus 10 is 24, and 8, 32. Yeah, okay, so this is balanced. Okay, so this is the reaction, and we must remember to balance it as well. So that's it. So the questions are not really hard, as you can see. It just, but you do need to have read kind of all the details in the book, in the chapter. Okay, now this question now actually involves mole calculations, which is not difficult really. The equation for the complete combustion of ethene is shown. So here is the equation they give it to us ready. Calculate the volume in cubic decimeters of carbon dioxide formed. So we need to find this volume here of carbon dioxide in the complete combustion. Yeah, this is a complete combustion of 1 gram of ethene. So we have 1 gram. If 1 gram of ethene is combusted completely, what would be the volume of the carbon dioxide produced? And obviously we can see more calculations here, isn't it? And also because carbon dioxide is gas here, and they ask for volume, obviously our mind has to go straight to the molar volume. 1 mole of any gas, 1 mole of any gas always occupies the same volume, which is 24 cubic decimeters, provided the conditions of at room temperature and normal pressure. Okay, at room temperature and pressure, yeah. Okay, so the conditions are right. So we know that 1 mole of carbon dioxide will occupy a volume of 24 cubic decimeters. Now, okay, well, how do we start? We have first of all the ratios of moles reacting here is 1 what is this ethene to 2 moles of carbon dioxide. So let us find how many moles of ethene is the 1 gram that we are given here. Now the relative molecular mass of ethene is what is carbon is 12, so we have 2 carbons, 2 times 12 plus hydrogens 4 times 1. The 1 and the 12, obviously, I hope you remember, are the relative atomic masses of carbon and hydrogen respectively. And this is 28. That is the relative molecular mass of ethene. All right, so this one mole of ethene, in other words, is 28 grams. So 1 mole of ethene, let's write this way, is 28 grams. The 1 gram that we have here, how many moles is that? We solve for x, that would be 1 over 28 moles, isn't it? And we can leave it like that, or if we divide it, this is 0.0357 moles. There is no need though to do this calculation. We can keep it as a ratio, and we can replace it as that. Okay, now we have, these are the moles of things that react. And obviously the carbon dioxide produced is double the number of moles. So how many moles of carbon dioxide is that? It's twice 1 over 28. So it's 2 over 28 moles of carbon dioxide produced, isn't it? So we know now that 1 mole of carbon dioxide of any gas is 24 cubic decimeters, occupies this volume. So the 2 over 28 moles, how much volume do they occupy? And again, if we solve for x and do the calculations, that will be 2 over 28, yep. So this gives us 1.7 cubic decimeters, and this is the volume occupied, the volume of the carbon dioxide produced. So the volume of carbon dioxide produced here is the 1.7 cubic decimeters. So this is from the first chapter revision. All right. Now, okay, this is the first page of this question, and this was not really terribly difficult, isn't it? But now let us go to the second page, which continues again with alkanes, and now let us read carefully what they say. Now they give us this table. Let's see. The table compares the reactivity of alkanes and alkenes with chlorine. So how they react with chlorine, all right? And they say that the name of the type of reaction with chlorine for concerning the alkanes. When alkanes, in other words, react with chlorine, the reaction type is substitution. It's actually the free radical substitution, if you remember. So actually, and what is the second row? Says the name of the type of reacting species. The free radical here. So it's a free radical substitution. This is the type of reaction when an alkane reacts with chlorine. Now, when it comes to alkenes, when alkenes react with chlorine, what types of reactions do we have? We have these reactions can be addition reactions, but also substitution reactions. And what type of, what are the reacting agents, reagents there? Name of the type of reacting species. Electrophile, they say electrophile. They refer to the addition reaction. Remember electrophilic addition of alkenes, if you remember the mechanism of the reaction that we've done. So electrophiles are one type of reacting species. And for the substitution, it's also free radical. We can see that alkenes can also react through free radical substitution like the alkanes, although we have not met examples of that. Nevertheless, they give us this table, so we take it for granted. And now I suppose, let's see, this question must refer to this table. The first question says, during the first stage in the substitution reaction, chlorine forms chlorine-free radicals. Okay. The first stage of the substitution, yeah. Explain what is meant by the term free radical. What is meant by the term free radical? If you remember the free radicals. Free radicals, we say it's a species that has one unpaired electron. Because if you remember, when the chlorine molecule is found under UV light, it might break. It might break, and these two electrons that that are part of the bond between the two chlorine atoms, actually this bond breaks through the influence of the UV light, and one electron goes with one chlorine, the other electron goes with the other chlorine atom, and these two chlorine atoms now that are formed, two of them, are free radicals, and they are very, very active. So our answer here is that a free radical is a species with one unpaired electron. A species with an unpaired electron. Not to write the whole word, electron. Okay, it's just one question, just a sweet and short answer. Then the next question says now, name and explain the type of bond breaking which occurs to form chlorine-free radicals. In other words, this breaking of the bond. What is the breaking of the bond? We call it homolytic fission. They want to see the word homolytic. Homolytic fission. Fission means the breaking of the bond. Homo is because homo means same. It's the same type of, how can we say, the breaking is the same for both species involved. One electron goes to each chlorine atom here, for example. So the pair of electrons between the two chlorine atoms is shared equally in the same way. That's why it's called homolytic fission. So this is the homolytic. Name and explain the type of bond breaking. Yeah, homolytic fission, this is the name, and we can say that one electron goes to each chlorine atom. One electron goes to each chlorine atom. Okay, so that is the explanation. Name the stage of the reaction. Now, name the stage of the reaction mechanism which occurs when a methane molecule reacts with a chlorine-free radical. Now when we have one methane molecule that reacts with a free radical here, chlorine-free radical, what happens here? Sorry, no, they ask what is the name of this. Name the stage, right? This happens in the second stage, actually, after the initiation stage, where the chlorine molecule breaks into two free radicals. So the second stage is actually the propagation stage. So this is the propagation stage, the propagation stage, all right? Then complete the equation for the reaction which occurs when a methane molecule reacts with a chlorine free radical. Also here we have to complete the reaction. We have now the free radical. Remember, these are very active and attack the methane molecules. And what happens now, this chlorine will join with one of the hydrogens of the methane and will give us hydrogen chloride. And what will remain behind is it will be this free radical, a methyl free radical, methyl free radical, which will become now active by itself and can continue now. This can attack now a chlorine molecule and produce more free radicals, if you remember. But nevertheless, this is what they want us to write here, and here's where we stop. They just want us to understand what's going on with the free radicals, because this is how one can break the molecule of an alkane with the free radicals. Otherwise, the alkane molecules really are very unreactive because they are very stable. They have they're unsaturated. They don't have space for extras to add. So that's one way to change them, is to attack them by free radicals, isn't it? So carbon, the next question, carbon atoms can form sigma and pi bonds with thin hydrocarbon molecules. Explain the following statement with reference to sigma and pi bonds. Alkenes react with electrophiles, but alkanes do not. So we need to explain what is going on. So we need to say, first of all, what is the difference between alkanes and alkenes? The alkanes, all the bonds in the alkanes are single bonds. In other words, they're sigma bonds. Alkanes have sigma bonds, okay? And whereas the sigma bonds, which are single bonds. Now, the alkenes, on the other hand, the alkenes have both sigma and pi bonds, because the characteristic is a double bond of carbon. One of these bonds, now, one of these bonds is a pi bond, the double, and the single bond is the sigma. What am I saying now? They have a sigma bond and a double and a pi bond. The pi bond is responsible for the double bond that we see in the alkenes. And one thing which is very, very important with the double bonds is that they are electron-rich centers. They are considered to be electron-rich. And so that double bonds are electron-rich centers, which we can also call them nucleophiles. Nucleophiles. And therefore they attract electrophiles. So we can say electrophiles are attracted to these double bonds. So they attract electrophiles species, electrophiles. So this is the difference between the alkanes and alkenes. The alkanes, the single bond is not an electron-rich center. It's a neutral kind of center in terms of positive or negative polarity. There's no, it is not considered any electron-rich anything. But the alkenes, on the other hand, the double bond that we find in the alkenes is a very electron-rich center and attracts electrophiles. And this is what we need to write here. So these 2 marks, actually, we have to explain what is the difference between alkanes and alkenes in terms of their bonds, sigma and sigma plus pi bonds, and that the fact that the double bonds is an electron-rich center and it attracts electrophiles. This is the second mark from these 2 marks that we have here. Okay, so this is one question that involved alkanes. Now, most of the questions we said, though, concern alkenes, and there's a lot of meat in alkenes. So let me change the exam paper here. So let us go to, let me see, what is the next question? Okay, let us see this question. Now, when it comes to alkenes, because of their double bond, they have a lot of meat here to discuss and for questions to ask. And one type of question that comes very often is about their oxidation. If you remember the oxidation with when they use manganate ions, acidified manganate solution, acidified, which means is dissolved in acid and with also manganate ions. So, but it makes a difference whether this is cold and dilute or if it's hot and concentrated, because the results of these oxidations will be very different. So three alkenes, X, Y, and Z, have the same molecular formula, Describe what is seen with aqueous bromine. Describe what is seen when aqueous bromine is added to X. Aqueous bromine. Yeah, you see that whenever there are tests of something, to test for something, to distinguish between different compounds, you need to remember all those tests. They will ask for them always here and there. So one of these tests is this decoloration of the bromine water. If we add when aqueous bromine, what did I say now? If we add aqueous bromine to some X, some alkene X, if it is an alkene, it will react with the bromine water because of an electrophilic addition. Bromine will be added to the alkene, and it will change. It will become a halogenol alkane, and the bromine water will change from this yellowish brown that it is to colorless. So we know that if there is this change there, if we see from the yellowish to orange color to change into colorless, we know that this was an alkene, an unsaturated hydrocarbon, in other words. So the decoloration of bromine water is common test for to test if a compound is unsaturated or not. So in this case, because we know that these are alkenes, which means they are unsaturated, we know that the color of the bromine water will change. And from this orange-brown that it is, let's call it orange-brown. The orange-brown aqueous bromine solution will change to colorless. Yeah, without colorless. Okay, so this is what will happen. It will change color because the bromine will be added to the alkene. All right, so next, what is it saying? X, Y, and Z are reacted separately with hot, concentrated, acidified manganate. Oh, there we go. Of course, there's the oxidation here with the manganate, and they say hot and concentrated. It's important to tell us the conditions because we need to know the product. Where am I now? Hot, concentrated, acidified manganate ions. Until no further reaction occurs, the carbon-containing products are shown in the table. Okay, so these are the products that we get after the alkenes have been oxidized. The alkene X gives us these products, the Y these products, and so on. Now look at this. Now this is actually an acid. I hope you remember that this part now corresponds to is the functional group of carboxylic acids, isn't it? The functional group of an acid. This and this one as well. This is also a carboxylic acid. And this top one, this compound here, look at this. It's actually a ketone because look at this carbon here. It's connected to this oxygen, and it's also connected to two other methyl substituents here. You see that? I hope you see that this is a ketone, and these two are acids. But there's also carbon dioxide in some of them. So these are the acids we have here. Okay, so these give us clues of what type. What do we need to find out here? They're reacted separately in hot and concentrated acidified manganate ions until no further reaction occurs. The carbon-containing products are shown in the table. Draw the structures. Draw the structures of X, Y, and Z. From this information, we can find the structures. Now, it needs some thought here. It's not like, importantly, we need to remind ourselves what is happening with the alkenes and when they're oxidized with hot and concentrated manganate, acidified manganate ions. Okay, so we need to remember that in general, alkenes have a double bond. Okay, and the products, what we're going to get out, depends on what is connected here in the two carbons which are involved in the double bond, isn't it? We need to remember that, for example, it's in the book. I'll show you here. You need to learn this very, very carefully. I don't know where they are. Page 210. Yeah. Okay. This you need to remember them very well and to learn by heart. So we see that when we have two hydrogens, when these two substituents of one carbon are two hydrogens, these, after the oxidation, will end up forming carbon dioxide and other things, of course, depending on the other side as well. But let's look at each side of carbon, part of a double bond. So here we see already there are two carbon dioxides, which means that one side of one carbon of those two must have two hydrogens there, like this one. Then, if we have one hydrogen and one some kind of alkene connected, if the one, for example, is a hydrogen and the other one is some kind of alkene of any sort, then the product here will be an aldehyde, which will further be oxidized with reflux into acid. So since we have two acids here, both the Y and the Z, this tells us that the Y and the Z compounds must have one carbon connected to one hydrogen and one other type of alkene here. Okay, so because these ones will give us, first of all, the first oxidation will give us actually an aldehyde. Obviously, this will be an aldehyde since the one's here, since the one is hydrogen and the other one is some other alkene. You see, this is the functional group of aldehyde. But usually, when we have aldehydes, these oxidize further in the presence of this hot and concentrated acidified manganate, and therefore this oxidize further into a carboxylic acid that corresponds to this aldehyde. And what will be the result? We'll have of course, the carboxylic acid here, and here will be this alkyl constituent, substituent of this carbon here. So you see, because we have here in this Y and Z, the one product is a carboxylic acid. So obviously this is what has happened here. This is a carboxylic acid that they are talking about, and this is the product of some alkene that had this form, had one carbon was connected to one hydrogen and some other alkyl substituent. So already we get an idea, which is enough actually to answer this question, but let us discuss the third possibility of the oxidation of an alkene, where both of these are some type of alkyl groups, and we have no hydrogen in one of these. In this case, the product will be a ketone, and the product will be a ketone. We don't have a ketone. Oh no, we do, don't we? The first one is a ketone, yeah. Oh, there is a ketone, yeah. So, okay, we're going to need this one as well. So this is a ketone, of course, because then this is the carbonyl group, the characteristic of ketone, and here are the alkyl substituents that appear in this alkene, which becomes oxidized. So there is our ketone. All right, so we know, in other words, that the first compound that we are given, the X, must have in one side, look at this, we have, hey, for the first compound, we have carbon dioxide produced, which means one of those carbons has is of this type, is connected to two hydrogens, and then we have a ketone produced over here. Here's our ketone, and what is our ketone? According to this formula, this is our ketone. You see, there are two alkyl groups connected to the other carbon. So what is the structure of this X? We know one side has two hydrogens, the other side has these two methyl substituents. So this will be, we can write it like that, the two methyl substituents, two of them connected to this carbon, and the double bond, and the other carbon is connected to two hydrogens because the product is carbon dioxide. So here we have two hydrogens. So I hope it makes sense how we find it. Now, in the second compound, we have a carbon dioxide produced, which means one carbon is connected to two hydrogens. So, and the other side, look at this, we have an acid produced, which means we are in this category where one carbon is connected to one hydrogen and one alkyl group. And which alkyl group? We'll find it from here, obviously. So this, if we start from this big alkyl group first, which is all that. So its structure will be carbon 2 of all that, then this single hydrogen, which is this one, and then is a double bond here, and the other side has two hydrogens, so carbon with two hydrogens. Okay, why am I writing so high? I don't know. And the Z now compound. In the Z compound, we have the formation of a ketone. And when we have a ketone formed, this ketone comes from the fact that the carbon is connected to two methyl groups, not two alkyl groups, whatever groups